Okay, so continuing on with class 12. This is video 2. Video 1 was excessively long, and I hope maybe somebody watched it all the way to the end. Maybe somebody did. Who knows? So here is an example of an orifice meter. This is coming right out of Sengel. It's an example. It's Sengel's example. And they're going to measure the flow rate of methanol at 20 degrees Celsius, which they've given us the fluid properties of 788.4 kilograms per cubic meter, and a dynamic viscosity of 5.857 e to the minus 4 kilogram meter second. 1 second, please. Okay, so I just wanted to check that these units that I have on the exam equation sheet, which is right here, right? So we use, for dynamics viscosity, we use a Newton second per meter squared. It bothered me that they were providing in kilograms, kilogram per meter second. So here's their units. Here's the units I'm using. We could replace the Newton with a kilogram meter per second squared, right? Because that's F equals MA, right? And by putting in there, we could see that the meters would cancel out right there, so that we left a meter on the denominator. Second would cancel out, so we left in a second. So this is the same unit as that. It always bothers me, so I think it's a good thing to check that we're dealing with the same units right here, that we don't have to apply the acceleration of gravity there. Through a 4 centimeter pipe, right? So this is a 4 centimeter pipe, and it's measured using a 3 centimeter diameter, right? So that's the diameter of the orifice. Equipped with a mercury manometer, right here, this mercury, right in there, across the orifice plate. If the differential height of the manometer is 11 centimeters, determine the flow rate of methanol through the pipe and the average of velocity. So we can use a beta right here. We could get that ratio. We're going to need that in a little bit, but that really kind of typifies what kind of orifice this is. So it's going to be 3 centimeters divided by 4 centimeters, or 0.75. We're going to need to use a manometer here. So let's get the, for whatever reason, I got the I want the density of the density of mercury. So I looked that up as 13,600 kilograms per cubic meter. Okay. I wanted to get the areas of these two things. I'm going to need them later on, at least one of them. So I'm going to get the area coming in, pi over 4, and it's a 0.04 meters squared. So that's 1.257 e to the minus 3 meters squared. A2, pi over 4, 0.03 squared, 7.069 e minus 4 meters squared. Okay, so there's some preliminary stuff. I want to get what the pressure difference is between these two. So you got to be a little careful here when doing the manometer. Just be advised. What I like to do, they don't give you this dimension, but I like to call it something, and I decided to call it L for no apparent reason, because I want to do the swim thing that we talk about. Right? So I want to see the pressure between 2 and 1. So I say that if I want to find the pressure at 1, I start at 2 and I swim to 1. So I get the pressure at 2, and I'm going to swim down this length right here. And so I'm going to go downward, so it's positive, that length. And then I'm going to take the specific weight of methanol. I'll call it meth. It's not that kind of meth. And then I'm going to swim an additional amount down. And that's going to be my H of my mercury. So there you go. And now I'm going to swim up. So I have to be, so I'm going to go minus, and the distance I'm going to go this H plus L plus H, right? So there's H and the L all the way back up through the methanol. And I'm going to find that if I had just said, okay, well, this has to be the pressure difference between here, we would be off, slightly off. So just be aware right here. So I'm going to go this P1 to P2. That's really the pressure that I care about. And we're going to see that I'm going to have this minus L and this plus L. So that's going to go away. But what we're left with is we're going to have H, and we have the gamma of the mercury minus the gamma of the methanol. So notably, that's going to be H times G, and now I'll go the density of the mercury minus the density of the methanol. And I could figure out what that value is right now because I'm given this, right? I'm given what this H is. That's in 11 centimeters. I know G and I know these densities. But I went ahead and I waited to put them into my equation for whatever reason. One of the issues that I'm going to have for my main equation, let me write my main equation out, is going to be CD times A2 square root of 2 times P1 minus P2 divided by rho 1 minus beta fourth. My big issue is that in order to find this CD, this coefficient, I need to know the Reynolds number. And to know the Reynolds number, I need the velocity. But to know the velocity, I need the volumetric flow rate. So we got ourselves a paradox. The only thing we can do is iterate. So what we do, I think, most of the time, this is what I advise you to do, is to pick a number from the middle, right? So let me rotate this around and show you clockwise right here. I'm going to pick a point that's, we're in the orifice right here, somewhere in the middle of this, so 0.62. Arbitrarily pick a value to start out with. So this is going to be my first guess. So I'm going to put G here for guess, or maybe sometimes I write guess. Here's my first guess, and I'm going to put in here 0.62. Right, guess underneath it. My area 2 is going to be 7.069 e to the minus 4. My square root here is going to be 2. And now I'm going to replace this guy right in here. And I could have done it all along. So I have my 11, right? And so that's going to be 11 centimeters. So that's actually 0.11 meters. And my G, 9.81. And my density here of mercury is 13,600. Put parentheses in there. And we're going to be subtracting out our methanol density, which is 788.4, right? So it's not unsubstantial that we would need to do that subtraction, which we would only know by way of doing this manometer swim through method. Now we're dividing by the density right here. So we get 788.4. And then 1 minus our beta is 0.75. Fourth right there. Now, save yourself some time because none of this stuff right here is going to change. Only that's going to change. So maybe calculate this and write it over to the side because we're going to go through the process of guessing this number, right? So this first guess is going to give us a flow rate of 3.134 e to the minus 3. These are cubic meters per second. So the velocity that we're going to get, we want the upstream velocity to be able to get, let's go back to this right here. We need the Reynolds number right here, and that's the upstream velocity right here. So for this, I'll write a guess. I don't know why I went for big G for right there. We're going to take that, divided by A1. So I got 3.134 E minus 3. And we're dividing it by that area that we got up at the top, right? So I told you why I was getting those right at the beginning. Oops. And we're left with 2.494 meters per second. And so the Reynolds number, and once again, this is from our guess, is going to be equal to rho VD over mu. So 788.4, 2.494 times point, and these are the diameter of the pipe, so it's 40 centimeters, right? So did I do this wrong? It'd be 40 millimeters. No, it's 4 centimeters. Okay, so good. Well, okay, there's 4 centimeters. Good, I got that right. Okay. Started to second guess myself. And here's the dynamic viscosity that we got, 5.857 E minus 4. So we're left with 100, and looks like 134, 300 is our Reynolds number. We could go to and do this graphically, and I was thinking maybe I would suggest it because I'm looking how long this problem takes, and I don't want you to suffer too much through the hand calculations. One little trick that you could take is you could take log to the base 10 of that value, because this is a log scale right there. So if you take 134, 300, and you go log of the thing, and let me find a log base 10, you get 5.128, right? So I'll write onto this thing. Let's see, right onto there. Let me close that down. So that means that we're going to have 5, and like here is 5.5, and here's 5.25, here's 5.125. So, and you'll see that we have this right here. So we're going to be somewhere. Oh, I'm on the wrong one. Darn. I'm on the nozzle. This is a orifice. Let's try it again. So here is 5.5, here is 5.25, and here's 5.15. And by the way, just to explain, I took 300, and I hit my shift here, and I did log base 10, and I got 5.125. So that would be 10 raised to the 5.128, and therefore that's why I am able to use that breakdown right in there to see between here. And so here's approximately where I want to go. And this is actually off of this graph, so we're gonna have a little bit of a problem here. We'll recognize that we have a little bit of a problem when we go to, especially when we notice from the Excel, but the best that we have is like right around here or thereabouts. About there, and you can see that we get like a 0.6125 or something like that. Somewhere like right in there. Okay, we can't really quite say. If I plug it in instead into that equation that I was given, and you can see from the previous video that there's an issue with that. That equation that was provided in Sengel, 5959 plus 0.0312, and that's the 0.75, and this is raised to the 2.1, right? So there's our beta, and minus 0.184 and 0.75 raised to the 8, and I don't know if this should be an 8 or a 6. I mentioned that in the previous video that I'm a little skeptical of Sengel's metering thing there, of its transcription. I think they might have written the wrong thing wrong, or that website did. I don't know. I showed you the website that has the has those factors for a lot of other configurations. So as I'm talking, I'm trying to look up if this version of Sengel might have fixed that previous version. because I was just looking at basing it on the first version of Sangle. I don't even see those values anymore. No, there they are, right there. Yeah, they have the same one right here. They're using the 8 in here. I'm suspicious of this information right here. I'm not sure if that's the right one, but that's the equation that I'm using. And I'm raising it to the 91.71. And here's the beta raised to the 7.5. And this is a raised to 2.5. All right. And then we have the Reynolds number of 134,300 raised to the 0.75, right? And for your information, once again, this is for the Orifice and all of those things. And I can't say that I've double checked it. It looks like it's right. But you could see from this, we get a CD of equal to 0.6009, right? And so remember that we used a guess right here of 0.62. So we would get the updated, maybe this is I say the first iteration. That's what I'm saying. We got a 0.6009 multiplied by our 5.055 E minus 3. And our update is 3.037 E minus 3. And this is cubic meters per second. And by the way, that was 3.08% off from our initial guess, right? So we guessed that 0.62 and we were wrong. So we could do this again right here and find the velocity from our first iteration. And if we do that, we get 2.417 meters per second. And we get a new Reynolds number from our first iteration of 130,100. And therefore, we get a new CD from our first iteration of 0.6011. And then if we go now to our second iteration, and 0.6011 times 5.055 E minus 3, we end up getting 3.038 E minus 3, and that's really darn close to what we had before, so there's no point in doing further iterations. And so that's what we're going to say is our answer. Now, getting up to the upper levels of what I'm willing to do for a example problem. But let's see. Is this the same? This is they have a different. This is a different edition. So is this going to be example now 311 in this book? Yes. So the volume flow rate that they've calculated here, right? So I do my stuff separately, so I don't like just copy what's in the book. I want to look it up in myself, right? So here you go. Noticeably that here's your mercury minus your meth, and here is us applying that equation right in here and coming up with using 0.61. Right, so they decided to use 0.61. Why did they? Because they said this was our first guess. So we have a different guess as our first guess. And that's equivalent to this number of liters per second. That's a good thing to know. We get the speed, right? So what did our speed come out? Ours was 2.494. And so we get our Reynolds number. And then we substitute this Reynolds number into that equation, and they say they got 0.601. And they said that's good enough. So there you go. We have to do a little bit of an iteration, and I guess it really lends itself to doing something in Excel so that you don't have to plug everything into this every single time. So we'll move on to example 2.